Good morning. Thank you for joining Samsung's keynote today. I'm Yang Seok-ki, a Vice President of Memory Solutions Lab of Samsung Electronics at San Jose. It is an honor for me to have the opportunity to give a keynote in the Precision Memory and Computational Storage Summit 2022. Today, I'd like to share a new eco-friendly computing approach with the title of Innovation with SmartSSD for Green Computing. The key message I want to convey through this keynote is we need a new computing paradigm to reduce emissions in data centers. In the current situation, where large amounts of data are generated and a lot of computing power is required, data-centric computing using computational storage devices can be a promising alternative to green computing. First, let's talk about the relationships between climate change and data centers. Climate change is one of our most important problems. The photos on the left show the annual minimum of Arctic sea ice since 1979. At the end of each summer, sea ice coverage reaches its minimum extent. Since satellite record begins in 1979, the coverage has been steadily decreasing. The following photos in the center shows global changes in the carbon dioxide concentrations and distributions since 2002 in the altitude range of 1.9 to 8 miles. The yellow to the red area represent higher CO2 concentrations, while the blue to green area represent lower concentrations measured in parts per million. Last, the photo on the right shows the progress of Earth's surface temperature change. Dark blue indicate area cooler than average. Dark red indicate area warmer than average. As you can see, climate has deteriorated a lot. It is interesting to note that the data centers have not been a major contributor to this climate change. In fact, data centers did not use as much electricity as people guess, and the data centers have been doing relatively well so far. The graph on the left shows the data center energy index based on the energy consumption of 2010. As you can see, data centers use around 1% of global electricity, about 200 terawatt hours to 250 terawatt hours in 2020. And it has been almost flat since 2010 due to various technology innovations such as cloud and processor efficiency, even though the internet traffics and data center workloads are increasing exponentially. Then you will wonder why I'm talking about the climate issue in this keynote. Unfortunately, flat use of electricity is not enough. In fact, we must do much better for the next generation. The ICT sector has published a science-based pathway for ICT emission in the line with Paris Agreement compatible with 1.5 degrees Celsius scenario. Data center trajectory requires a 53% emission reduction by 2030. In response to this request, the Climate Neutral Data Center Pact was launched and developed by industry on January 21st, 2021. Data centers and cloud infrastructure providers are working toward climate neutrality by 2030, with 5 clear metrics to achieve in 2025 and 2030. These 5 metrics include energy efficiency, clean energy, water conservation, circular economy, and circular energy systems. Over these 5 areas, I believe suppliers of server components like Samsung can make a direct contribution to 2 areas, circular economy and energy efficiency. Especially, I will focus on energy efficiency today. To increase the overall energy efficiency of data centers, we need to pay attention to how to make server more energy efficient. Let's talk more about why. This graph, taken from a paper published in 2020 by Science, showed that the number of servers used in data centers has increased dramatically since 2010. And the servers have become a major component of data center power consumption, accounting for more than 50% of electricity usage. This means that reducing server power consumption is critical to meeting the emission target. Then, how can we reduce server power consumption? If we can deliver more computing power with the same electric power budget, fewer servers can meet our computing needs. A server's overall computing power can be determined by the server's computing density and its utilization. As you know, Moore's law made possible high-density servers with more computing power. The graph on the left shows that the number of transistors per square millimeters increases as chip processing technology advances. The graph in the center shows that as chip processing technology advances, it consumes less power for the same number of transistors. As a result, CPU processing power increased over time, as shown in the graph on the right, but power consumption has not increased much. How about server utilizations? Before cloud became popular, servers were provisioned for peak times and underutilized in normal situations. In this case, the static power consumption of servers cannot be neglected when the server is not heavily used. Virtualization and cloud technologies have reduced this idle time and significantly improved the overall server utilization. The graph on the left shows the data center power usage by data center type. Over 80% of data centers rely on cloud technologies or use hyperscalers. The graph on the right shows that over 92% of servers are already virtualized. After all, it can be seen that most of electricity was well used to perform meaningful computation. Then we must do much better than what we have done so far to cut electricity usage by additional 53% by 2030. How can it make possible? The CPU technology and the cloud allow efficient use of electricity. However, two theoretical foundations for higher server density have already been challenged. Linear scaling no longer works, and Moore's law is slowing down. Also, it is not realistic that server utilization can be significantly improved because most data centers are already cloud-based and most servers are already virtualized. Unfortunately, existing solutions seem to have little room for further improvement. For this reason, we may need an alternative solution. There may be several solutions to reduce power consumption and meet the growing computing needs. However, I argue that computational storage devices could be a promising solution to this problem. Then, what is computational storage device or CSD? CSD is a storage device with processing capabilities that improve system efficiency. In other words, it is a comprehensive concept that increases overall system efficiency by performing some or all of the functions processed by existing CPU in CSD. Depending on the primary purpose, system efficiency can be improved through offloading or acceleration. Offloading mainly aims to reduce CPU load by leveraging the low power processing unit of CSD. It is mainly performed for background or offline work with low power and low real-time requirement. Acceleration, on the other hand, is primarily focusing on improving the performance of foreground or online operations with strong real-time requirement by leveraging higher throughput than CPU at given power budget. What are the potential benefits of computation storage devices? Simply put, CSD can provide scalable, low-power processing with a low bandwidth footprint at the rack level. First, CSDs typically use low-power components. For example, ARM RISC-V, MPU, FPGA, or ASIC are used as a processing unit. Computation storage devices allow the system to reduce host resource utilization while computing is being performed, thereby saving system power consumption. Second, computation storage devices can significantly reduce the amount of data passing through the system because only filtered or refined data leaves the storage after it is being processed. For example, CSD can be used to filter or compress data. This means that the system will use less power for host CPU or DMA, and the I/O bus or network will be less congested. It can also improve host CPU cache and the network utilization. Third, CSD uses the device's internal bandwidth, which is less influenced by external constraints. For example, it is less affected by bandwidth and utilization of device interface, PCI bus, network, or RAID, or eraser coding. Finally, as more devices are added, the overall computing power increases proportionally. Again, the actual storage bandwidth available to application is limited by the bandwidth and the utilization of PCI bus or network. For this reason, a large number of storage devices in a storage system mostly contribute to storage capacity, but limitedly contribute to storage bandwidth or computing power. In the previous slide, I presented the potential for power reduction and performance improvement when CSDs are used. Let's be a little bit more specific. To understand how CSD can help increase server density, we conducted a roofline performance study based on one possible CSD architecture. Given a standard rack power budget, this study determined the power balance between CSD and server CPU for maximum server throughput. That is, when a rack power budget is fixed, the TCOs of two racks are calculated. A standard rack is populated with 2U servers as shown on the left, with each server node configured as shown in the center. The SSD used in the server nodes are identical in capacity and performance, except for computing functions of CSDs. Specifically, the CSD architecture determines what kind of benefit can be achieved. The CSD architecture used in this study assumes a computing performance and the efficiency similar to Fujitsu A64FX CPU. A cluster of ARM processors are connected to high bandwidth memory and the PCI Gen 4x4 based SSD as shown on the right. The graph on the left shows the impact on overall server performance when power is distributed to balance performance across processing units and memory. The x-axis represents the arithmetic intensity of application, and the y-axis represents computing throughput and memory bandwidth. As the graphic shows, as the arithmetic intensity increases, the processing throughput quickly saturates to the power limit. And as the throughput saturates, the memory bandwidth consumed also decreases sharply. From this graph, we can see that CSD can only efficiently handle I/O-intensive applications. Therefore, it is important to provide sufficient I/O bandwidth, which is limited by either memory or NAND bandwidth, depending on the CSD architecture. For these I/O-intensive applications, Roofline study shows that CSD-based server can be more economical and eco-friendly than regular SSD-based servers, which deliver up to 47 to 70% better performance per dollar per watt. As a result, CSD can provide higher server compute density than x86 CPU-based solutions. To realize this vision, Samsung took a bold step 2 years ago and commercialized the SmartSSD CSD. The first SmartSSD CSD product was released in 2020. Let's take a closer look at its architecture. Based on PCI Gen 3, the SmartSSD offers 4 TB of storage capacity and 4 GB DDR4 of device memory space in a U2 form factor. It also adopts FPGA to increase computing power and application flexibility. FPGA provides around 300K lookup table to implement custom IPs. There is also a special PCI lightweight bridge implemented in FPGA. This bridge allows a single device to be used as both NVMe device and FPGA accelerator simultaneously. In particular, the bridge plays a very important role in data transfer. The FPGA can communicate directly with the SSD without host intervention once the source and destination are set by the host. This can remove potential bottleneck on the host PCI bus and enable scalable computing with more devices. Studies conducted with several startups have confirmed that CSD can provide better TCO and scalability for a variety of applications and systems. First, a video transcoder on SmartSSD shows CPU utilization have improved by 23% and performance by 80% compared to older systems. Second, SmartSSD has also been applied to cyber forensic applications. SmartSSD has the scan done in just 25 minutes, while the current system takes several orders of magnitude longer. Meanwhile, when SmartSSD was applied to IDT-Com's low-load file system, a relational database was able to save more than 3 times storage space without performance degradation. Finally, SwarM64 implements a scan engine on SmartSSD and allows users to achieve comparable performance at 1/3 the price of Amazon Redshift or PostgreSQL. As seen in the video transcoding and the cyber forensic examples, it is important to note that computational storage device increases its computing power linearly as number of devices increases. In other words, as storage capacity increases, computing power naturally increases as well. Samsung continued to invest these technologies, and the next generation of SmartSSD will be available soon. The most important lesson from a series of studies and product effort is we need friends to travel with to make technology successful and scalable. Our next generation device is focusing on developing a platform that enables various collaborations and technologies. The platform is built on 2 main design concepts. One is bring your own IPs, and the other is software-defined. The bring your own IP concept will expand hardware capabilities through collaboration and make computational storage features rich. On the other hand, software-defined concept make it easy for users to use these devices and for software engineers to expand device functions. Based on these 2 design concepts, next generation devices will be made comparable but competitive. The device supports standards such as NVMe TP4091 and SNIA computational storage API. We also plan to release a software development toolkit later this year that includes a library that is compatible with SNIA computational storage API and device driver that is compatible with NVMe TP4091. On the other hand, security and the multi-tenancy in the cloud are known, and device will have several system-level security features, including advanced encryption standard. Finally, one of the most challenging issues with computational storage is to handle different data formats in terms of data organization, compression, encryption, and more. Not all formats can be supported very efficiently, but this device accelerates some popular formats. Applications have different performance characteristics. SSD has limited application, and this device alone cannot solve the emission problem. Therefore, I'm proposing the concept of federated data-centric computing to increase computing efficiency and reduce emissions, and I hope to collaborate across industries. According to its state, data can be classified into data at rest, data in transit, and data in use. In the past, CPUs were used universally, regardless of data states. However, now there are many domain-specific architectures that can efficiently process data in each state. The domain-specific architecture is purpose-built for power-efficient and high-performance data processing. Various NPUs, including GPU and TPUs, utilize memory hierarchy to process compute-intensive data efficiently. SmartNIC, DPU, Smart Switch, etc. can effectively process network acceleration functions such as packet processing, protocol processing, and storage network functions. Computational storage can effectively handle data transformation and the filtering function while data is stored to or retrieved from the storage. Samsung further suggests federated data-centric computing to address this problem. If we use such domain-specific architectures effectively and perform computation near the data, we may be able to efficiently handle large amounts of data in an energy-efficient way. For example, we can use Spark map operation in CSDs to perform simple filtering operation. Then TPU can perform aggregate operations or data distribution like shuffling across a cluster system. Finally, CPU or GPU can process data with high arithmetic intensity and produce final result. For best result, we need a common framework for partitioning and coordinating tasks for domain-specific architectures. I believe this can only be realized through industry-wide collaboration and open innovation. Samsung is ready to contribute technology and open to collaboration. Let me conclude my keynote speech. Improving server energy efficiency is critical to reducing emissions by 53% in data center by 2030. Now that existing CPU-based innovations have been well established, it is time to leverage domain-specific architectures to meet the emission target. Computational storage devices are promising green computing solution for I/O-intensive applications. I believe that federated data-centric computing across different domain-specific architectures, including computational storage devices, can improve the energy efficiency of data centers. Let's work together to reduce emissions. Thank you for listening.